In the vast expanse of space, where countless stars twinkle like diamonds against the velvet darkness, there exists something far more mysterious than anything we can see. Beyond the glowing galaxies and shimmering nebulae, beyond the brilliant light of distant suns and the colorful dance of cosmic dust, lies a hidden reality that shapes everything we know. Imagine looking up at the night sky and realizing that everything you see, every star, every planet, every wisp of glowing gas, makes up less than 5% of what actually exists. The rest, the overwhelming majority of our universe, remains completely invisible to us. It cannot be seen, cannot be touched, cannot be detected by any camera or telescope. Yet without it, nothing we see would exist at all. This invisible universe is dominated by two mysterious forces. The first is called dark matter, an unseen substance that acts like cosmic glue, holding galaxies together with its gravitational embrace. Without dark matter, the stars would fly apart into the void, and galaxies would never have formed in the first place. It surrounds us, flows through us, and binds the universe together in ways we are only beginning to understand. The second force is even more puzzling. Dark energy is not matter at all, but rather a mysterious force that fills every corner of space. Unlike gravity, which pulls things together, dark energy pushes everything apart. It is the reason why the universe is not only expanding, but expanding faster and faster with each passing moment. This acceleration defies everything we thought we knew about how the cosmos should behave. Together, these two invisible forces make up 95% of everything that exists. Dark matter accounts for about 27% of the universe, while dark energy dominates with 68%. The stars, planets, and everything we can see represent just a tiny fraction of reality. But where did these mysterious forces come from? How did they arise from the birth of the universe itself? What role did they play in shaping the cosmos we see today? These questions have puzzled scientists for decades, leading them on a journey to the very edges of human knowledge. Tonight, we embark on a quest to understand the origins of the invisible universe. We will travel back to the first moments after the Big Bang, when the universe was smaller than a grain of sand, yet contained everything that would ever exist. We will explore the latest theories about how dark matter and dark energy came to be, and we will join scientists in their ongoing search for answers to some of the deepest mysteries in all of science. This is not just a story about invisible forces, but about the nature of reality itself. It is about the humbling realization that most of the universe remains hidden from us, and the incredible human drive to understand the unknown. As we journey through this cosmic mystery, we will discover that the search for dark matter and dark energy is really a search for our place in a universe far stranger and more wonderful than we ever imagined. The universe may be mostly dark and unseen, but its story is illuminated by the curiosity and determination of those who dare to ask the biggest questions of all. Where did the invisible universe come from? The answer may change everything we think we know about existence itself. The story of dark matter begins not with a grand theory or a brilliant flash of insight, but with a simple observation that something was terribly wrong with the universe. In the 1930s, a Swiss astronomer named Fritz Zwicky was studying a cluster of galaxies called the Coma Cluster, located roughly 300 million light-years from Earth. What he discovered there would shake the foundations of our understanding of the cosmos and launch one of the greatest mysteries in modern science. Zwicky was measuring the speeds at which individual galaxies moved within this cluster. Using the principles of gravity that had worked perfectly for centuries, he calculated how fast these galaxies should be moving based on the amount of visible matter he could see. The math seemed straightforward and reliable. The more massive the cluster, the faster the galaxies within it should orbit around their common center of mass, following the same gravitational laws that governed planets orbiting the Sun. But when Zwicky made his careful measurements, something was drastically and inexplicably wrong. The galaxies were moving far too fast. racing through space at speeds that defied all expectations. According to his calculations, based on the visible stars and gas he could observe, they should have flown apart long ago, scattered into the depths of space like leaves blown by a cosmic wind. The gravitational pull of the visible matter simply was not strong enough to hold them together. Yet there they were, bound together in a stable cluster that had clearly existed for billions of years. The Coma cluster was not flying apart. It was not dissolving into the void. Instead, it maintained its structure, with hundreds of galaxies orbiting in what appeared to be a gravitational dance choreographed by some invisible partner. Zwicky faced a puzzle that would haunt astronomy for decades to come. Either the laws of gravity, which had successfully explained everything from falling apples to planetary orbits, to the motion of comets, were somehow fundamentally broken on the largest cosmic scales, or there was far more matter in the cluster than could possibly meet the eye. The choice seemed impossible, yet Zwicky made a bold decision that would prove prophetic. He chose the second option, proposing that some form of completely invisible matter was providing the extra gravitational pull needed to hold the cluster together. This was not ordinary matter that was simply too dim to see, but something fundamentally different, something that exerted gravitational force without emitting, absorbing, or reflecting any light whatsoever. Zwicky called this mysterious substance dark matter, coining a term that would become one of the most important concepts in modern cosmology. He estimated that this invisible matter must outweigh all the visible stars and gas by a factor of more than 10 to 1. The universe, Zwicky realized with stunning prescience, was mostly made of something completely invisible to human eyes and instruments. The implications of this discovery were staggering. If Zwicky was correct, then everything humanity had ever observed, every star that had ever shone in the night sky, every galaxy that had ever been photographed, represented less than 10% of all the matter that actually existed. The cosmos was dominated by a substance that remained completely hidden from view. For decades, Zwicky's discovery was largely ignored or dismissed by the broader astronomical community. It seemed too radical, too strange, too uncomfortable to be true. How could most of the universe be made of something we could not see, touch, or detect? Surely there was a simpler explanation. Some subtle error in the calculations or observations that would make this unsettling conclusion disappear. Many astronomers preferred to believe that Zwicky had made a mistake, that his measurements were flawed, or that some conventional astrophysical process could account for the unexpected motions he observed. The idea of invisible matter filling the universe struck many as scientifically unsatisfying, almost mystical in its implications. But in the 1970s, decades after Zwicky's groundbreaking work, American astronomer Vera Rubin began studying individual galaxies in unprecedented detail. What she found would not only confirm Zwicky's startling discovery but extend it to scales that made the dark matter problem impossible to ignore. Rubin focused her attention on spiral galaxies like our own Milky Way, using sophisticated spectrographic techniques to measure how fast stars moved in their orbits around the galactic center. She expected to find a pattern that had been observed countless times in our solar system, where planets farther from the sun move more slowly in their orbits, following Kepler's laws with mathematical precision. The expectation seemed entirely reasonable. Just as Mercury races around the sun much faster than distant Pluto, stars near the center of a galaxy should orbit much faster than those on the outer edges. The gravitational pull from the central bulge of stars should dominate the motion of the entire galactic disk, creating a predictable relationship between distance and orbital speed. Instead, Rubin discovered something that challenged everything astronomers thought they knew about galaxies. Stars on the outer edges of galaxies were moving just as fast as those near the center, and in some cases they were moving even faster. This should have been completely impossible according to the known laws of physics. Without enough mass concentrated in the center to provide the necessary gravitational pull, these outer stars should have been flung into intergalactic space eons ago, like stones released from a sling. The galaxies should have unwound themselves, their spiral arms dissolving as stars escaped into the void. Yet every galaxy Rubin studied maintained its structure and shape, defying the predictions of conventional physics. Galaxy after galaxy showed the same impossible pattern. The rotation curves, as astronomers called these plots of orbital speed versus distance, remained stubbornly flat across the entire disk of each galaxy, instead of dropping off as all theories predicted. It was as if each galaxy was embedded in a vast, invisible halo of matter that extended far beyond the visible stars, providing the gravitational anchor needed to hold everything together. Rubin's meticulous observations, carried out night after night at observatories around the world, painted a remarkably consistent picture. Every spiral galaxy she studied showed clear and undeniable evidence of dark matter. The rotation curves were not anomalies or measurement errors, but fundamental signatures of the invisible universe that surrounded and permeated everything we could see. The implications were staggering beyond imagination. Not only did dark matter exist, as Zwicky had proposed decades earlier, but it appeared to be the dominant form of matter in the universe. The stars, planets, and gas clouds that made up the visible cosmos were merely a thin frosting on a vast cake of invisible matter. As word of Rubin's discoveries spread through the scientific community, other astronomers began conducting their own observations. The results were always the same. Galaxy after galaxy, cluster after cluster, showed the unmistakable signatures of dark matter. The evidence was overwhelming and undeniable. The evidence continued to mount throughout the 1980s and 90s, as new observational techniques revealed dark matter's presence in ever more dramatic ways. Gravitational lensing, the bending of light around massive objects predicted by Einstein's theory of relativity, provided a way to map the distribution of dark matter directly. When light from distant galaxies passed through galaxy clusters, it was bent and distorted by the gravitational field of the intervening matter. By studying these distortions, astronomers could create maps showing exactly where the mass was located, whether visible or invisible. Time and again, these maps revealed vast concentrations of dark matter that far exceeded the visible matter in the same regions. The invisible universe had finally been made visible, at least indirectly. Computer simulations of galaxy formation provided even more compelling evidence. When astronomers tried to model how the universe evolved from the smooth conditions of the early cosmos into the rich tapestry of galaxies and galaxy clusters we observe today, they found that visible matter alone could never have done the job. Only with dark matter could the universe have assembled itself into the complex structures we see around us. By the turn of the 21st century, the existence of dark matter was no longer seriously questioned by mainstream astronomers. Multiple lines of evidence from completely different types of observations all pointed to the same revolutionary conclusion. The universe contains roughly 5 times more dark matter than ordinary matter. Every star, planet, and living being exists within a vast ocean of invisible particles that interact with ordinary matter only through the force of gravity. Yet even as the evidence for dark matter became overwhelming and undeniable, its true nature remained completely mysterious. Scientists knew that dark matter existed, they knew roughly how much of it there was, and they knew something about how it was distributed throughout the universe, but they had no idea what it actually was. What were these invisible particles that filled the cosmos? How did they form in the early universe? Why did they interact so weakly with light and ordinary matter that they remained completely invisible? The discovery of dark matter had solved one cosmic mystery, only to create an even deeper and more perplexing one. The search for answers would lead scientists on an extraordinary journey into the most fundamental questions about the nature of matter, energy, and reality itself. They would build detectors deep underground in abandoned mines, launch telescopes into the cold vacuum of space, and construct particle accelerators capable of recreating conditions from the first moments after the Big Bang. The hunt for dark matter had begun in earnest, and it would take researchers to the very edges of human knowledge and beyond, challenging our most basic assumptions about the universe we inhabit. With the overwhelming evidence for dark matter's existence firmly established, scientists faced an even more profound and perplexing challenge. They knew it was there, they could measure its effects with remarkable precision, and they could map its distribution throughout the universe in extraordinary detail. But what exactly was this mysterious substance that made up the vast majority of all matter in existence, yet remained completely invisible to every instrument humanity had ever devised? Dark matter reveals itself only through its gravitational influence, like an invisible dancer whose presence can only be detected by watching the graceful movements of visible partners on the cosmic stage. It does not emit light of any wavelength, it does not absorb light that passes through it, and it does not reflect light that encounters it. In every conceivable sense of the word, it is truly dark, interacting with the electromagnetic force so weakly that it might as well be completely transparent to all forms of radiation across the entire spectrum. This invisibility is not simply a matter of dark matter being too dim to see, like a distant star whose light has not yet reached us, or a cold planet that emits no light of its own. Instead, dark matter appears to be fundamentally different from ordinary matter in the most basic and revolutionary way possible. While ordinary matter is made up of atoms that contain electrically charged protons and electrons, dark matter seems to be composed of particles that carry no electric charge whatsoever. The implications of this fundamental difference are profound and far-reaching. Ordinary matter interacts with light precisely because it contains charged particles that can respond to electromagnetic fields. When light waves encounter electrons orbiting atomic nuclei, they can be absorbed, scattered, or reflected, creating all the rich and varied phenomena we observe in the visible universe around us. The brilliant glow of stars results from electromagnetic interactions deep in stellar cores. The spectacular colors of nebulae arise when starlight excites atoms and causes them to emit photons at specific wavelengths. The shimmering atmospheres of planets scatter and absorb sunlight to create the beautiful worlds we see through telescopes. Every aspect of the visible universe depends fundamentally on the electromagnetic interactions between light and charged particles. Dark matter, by stark contrast, allows light to pass through it completely unaffected, as if the light were traveling through empty space. Imagine trying to observe a perfectly transparent ghost that exerts no influence on the world around it, except through the subtle pull of its gravitational field. This is precisely the challenge that dark matter presents to astronomers and physicists trying to understand its nature and properties. Yet gravity alone, despite being the weakest of the four fundamental forces, provides a surprisingly detailed and comprehensive portrait of dark matter's behavior and distribution throughout the cosmos. Through careful analysis of gravitational effects on visible matter, scientists have learned that dark matter forms vast, diffuse halos around galaxies, extending far beyond the visible stars into the empty darkness of intergalactic space. These dark matter halos are not uniform or featureless, but possess complex internal structure and organization. Dark matter is concentrated more densely in some regions than others, creating a three-dimensional web of invisible matter that permeates the entire universe. This cosmic web provides the underlying architecture upon which all visible structures are built. Computer simulations of cosmic evolution reveal that dark matter played the absolutely crucial role of cosmic architect in the early universe, shaping the formation of every structure we see today. In the first few 100 million years after the Big Bang, when ordinary matter was still far too hot and energetic to form stable structures like stars or galaxies, dark matter was already beginning to clump together under the relentless pull of its own gravitational attraction. These early dark matter concentrations acted like invisible gravitational wells scattered throughout space, attracting ordinary matter and providing the essential scaffolding upon which galaxies would eventually form. Without dark matter to provide this fundamental framework, the universe would have remained a nearly uniform sea of hydrogen and helium gas, expanding and cooling, but never developing the rich complexity of stars, planets, and ultimately life itself. The intricate relationship between dark matter and ordinary matter in galaxy formation resembles the construction of a massive skyscraper. Dark matter provides the invisible foundation and structural framework that determines the overall size, shape, and stability of the building, while ordinary matter fills in the visible components that we can actually observe and study. The dark matter halo surrounding each galaxy determines its fundamental properties, including its total mass, its rotation speed, and its ability to retain gas and form new stars. Meanwhile, the ordinary matter within the halo condenses to form the brilliant stars, glowing gas clouds, and rocky planets that make up the visible galaxy we can photograph and analyze. This cosmic partnership between visible and invisible matter extends seamlessly to the largest gravitationally bound structures in the universe. Galaxy clusters, which can contain hundreds or even thousands of individual galaxies spread across millions of light-years of space, are completely dominated by dark matter that provides the gravitational glue holding these enormous systems together. The hot gas that fills the vast spaces between galaxies in these clusters, glowing at temperatures of millions of degrees, provides another powerful way to trace dark matter's gravitational influence. This gas, though invisible to optical telescopes, can be observed by X-ray satellites and radio telescopes, revealing the shape and strength of the dark matter's gravitational field. But what could dark matter actually be made of at the most fundamental level? The question has driven theoretical physicists to propose a wide variety of exotic possibilities, each more intriguing than the last. The most widely accepted theories propose that dark matter consists of an entirely new type of elementary particle, fundamentally different from anything included in the standard model of particle physics that describes all known matter and forces. These hypothetical dark matter particles would need to possess several very specific properties to match what astronomers observe throughout the universe. Understanding these requirements provides crucial clues about what dark matter might actually be and how it might eventually be detected and studied directly. First and most importantly, dark matter particles must be completely stable over cosmic timescales spanning billions of years. Since dark matter has persisted essentially unchanged for over 13 billion years since the Big Bang, whatever particles compose, it cannot decay into other forms of matter on any timescale shorter than the age of the universe itself. This stability requirement immediately rules out many known particles, which tend to be highly unstable and decay rapidly into other particles. Second, dark matter particles must interact extraordinarily weakly with ordinary matter and even with each other. If dark matter interacted strongly through electromagnetic or nuclear forces, it would clump together much more dramatically than observations suggest, forming dense concentrations that would be easily detectable. The fact that dark matter can apparently pass through itself and through ordinary matter with minimal interaction suggests that these particles experience only gravitational forces and possibly very weak nuclear interactions. Third, dark matter particles must have been produced abundantly in the early universe and must have survived in large numbers to the present day. Whatever process created dark matter must have been efficient enough to produce roughly 5 times more dark matter than ordinary matter, yet the particles must be stable enough that they have not disappeared through decay or annihilation over cosmic time. One leading candidate for dark matter particles goes by the descriptive name of weakly interacting massive particles, universally abbreviated as WIMPs in the scientific literature. These hypothetical particles would typically have masses tens or hundreds of times greater than a proton, making them much heavier than any ordinary atomic nucleus, but would interact with normal matter only through gravity and the weak nuclear force. The weak nuclear force is indeed one of the 4 fundamental forces of nature, but despite its name, it is much stronger than gravity, while still being far weaker than the electromagnetic and strong nuclear forces. Particles that interact only through the weak force would be extraordinarily difficult to detect directly, which would explain why dark matter has remained hidden despite making up most of the matter in the universe. WIMPs would be ancient relics from the very early universe, created during the incredibly hot, dense conditions that existed in the first tiny fraction of a second after the Big Bang. During this primordial epoch, the universe was so hot and energetic that particle-antiparticle pairs were constantly being created and destroyed in a cosmic dance of creation and annihilation. As the universe expanded and cooled, the production of new particle pairs eventually ceased, and most of the existing particles annihilated with their corresponding antiparticles, converting their mass back into pure energy. However, if the annihilation process was not perfectly efficient, a small residual population of particles could have survived to the present day, providing exactly the dark matter we observe today. The theoretical appeal of the WIMP hypothesis lies partly in its deep connections to advanced theories that attempt to unify the fundamental forces of nature into a single, elegant framework. Many extensions of the standard model of particle physics, developed to solve other puzzles in our understanding of matter and energy, naturally predict the existence of particles with exactly the properties that WIMPs would need to have. This remarkable theoretical convergence, combined with the compelling observational evidence for dark matter's existence, has made WIMPs the primary focus of intense experimental searches conducted in laboratories around the world. Scientists have invested enormous resources in building detectors capable of registering the incredibly rare interactions between WIMP particles and ordinary atomic nuclei. Another intriguing possibility is that dark matter consists of much lighter particles called axions, originally proposed to solve a completely different theoretical problem in particle physics. Axions would be produced abundantly during certain phase transitions in the very early universe and would have exactly the right properties to constitute the dark matter we observe today. Unlike WIMPs, which would be relatively heavy particles, axions would have extremely small masses, potentially billions of times lighter than even an electron. Despite their tiny individual masses, axions could still make up most of the matter in the universe if they were produced in sufficient quantities during the Big Bang. Axions would interact even more weakly with ordinary matter than WIMPs, making them extraordinarily challenging to detect through direct interactions with laboratory instruments. However, theoretical calculations suggest that under very specific conditions, axions might spontaneously convert into photons of light when exposed to strong magnetic fields, providing a potential pathway for their detection and study. This process of axion to photon conversion would be incredibly rare and would require enormous magnetic fields maintained over large volumes of space for extended periods of time. Nevertheless, several experiments around the world are attempting to create exactly these conditions in hopes of catching the faint light signals that would indicate the presence of axion dark matter. More exotic possibilities for dark matter include sterile neutrinos, which would be particles similar to the known neutrinos that stream constantly through our bodies from the sun and other cosmic sources, but even more weakly interacting and harder to detect. Other theories propose entirely new categories of particles predicted by advanced theoretical frameworks, like supersymmetry, or models involving extra-spatial dimensions beyond the three we experience directly. Supersymmetry is a beautiful theoretical framework that proposes that every known particle has a corresponding supersymmetric partner particle with different properties. Many of these supersymmetric particles would be excellent dark matter candidates, possessing exactly the stability and interaction properties required to match astronomical observations. Some of the most speculative theories even propose that dark matter might not consist of particles at all in the conventional sense, but rather might be a manifestation of modifications to the law of gravity itself on the largest cosmic scales. These modified gravity theories attempt to explain dark matter phenomena without invoking any new forms of matter, instead proposing that gravity behaves differently than Einstein's general relativity predicts when applied to entire galaxies and galaxy clusters. The search for dark matter's true identity has evolved into one of the most important and ambitious quests in modern science, combining cutting-edge insights from cosmology, particle physics, quantum mechanics, and advanced detector technology. Scientists around the world have constructed increasingly sophisticated detection systems designed to catch the incredibly rare interactions between dark matter particles and ordinary matter. These experiments must overcome truly extraordinary technical challenges. If dark matter particles interact as weakly as current theories suggest, a detector the size of an entire building might register only a handful of genuine dark matter interactions per year, buried among billions of background events caused by cosmic rays, natural radioactivity, and other sources of interference. Distinguishing these incredibly rare and subtle dark matter signals from all possible sources of background noise requires unprecedented sensitivity, sophisticated data analysis techniques, and careful shielding from every conceivable source of contamination. Many dark matter detectors are built deep underground in abandoned mines or specially constructed laboratories, surrounded by layers of lead, copper, and other materials designed to block unwanted radiation. Despite decades of intensive searching using increasingly sensitive instruments, dark matter continues to elude direct detection, maintaining its status as one of the greatest unsolved mysteries in all of science. Its gravitational effects throughout the universe are undeniable and precisely measured. Its crucial role in cosmic evolution is well established, and its dominance over ordinary matter is beyond question. Yet the fundamental question of what dark matter actually consists of remains tantalizingly unanswered, challenging our deepest understanding of the nature of reality itself. The hunt for dark matter represents one of the most ambitious and technically challenging scientific endeavors in human history. Despite making up 85% of all matter in the universe, dark matter has managed to remain completely hidden from direct detection, forcing scientists to devise increasingly ingenious and sophisticated methods to catch even the faintest trace of these elusive particles. The challenge of detecting dark matter is unlike anything science has ever attempted before. Imagine trying to catch raindrops that fall so rarely that only 1 or 2 might land in your backyard during an entire year. And when they do hit the ground, they leave such a subtle mark that you need the most sensitive instruments ever built just to notice that anything happened at all. This analogy only begins to capture the extraordinary difficulty of the dark matter detection problem. Scientists have approached this seemingly impossible task from multiple angles, building 3 fundamentally different types of experiments, each designed to exploit a different aspect of dark matter's potential interactions with ordinary matter. These complementary approaches offer the best hope of finally solving the dark matter mystery and revealing the true nature of the invisible universe that surrounds us. The first approach involves constructing direct detection experiments deep underground, far from the constant bombardment of cosmic rays that rain down on Earth's surface every second of every day. These cosmic rays, which are mostly high-energy protons and atomic nuclei accelerated by distant supernovae and other violent cosmic events, create a constant shower of particles that would completely overwhelm any attempt to detect the much more subtle signals from dark matter. To escape this cosmic interference, scientists have built their most sensitive dark matter detectors in some of the most remote and isolated locations on Earth. Deep underground laboratories carved into solid rock beneath mountains provide natural shielding from cosmic rays, reducing the background radiation by factors of millions compared to surface conditions. One of the most ambitious of these underground facilities is the Sanford Underground Research Facility in South Dakota, built in what was once the deepest gold mine in North America. Nearly a mile beneath the surface, surrounded by billions of tons of rock, scientists have constructed chambers containing some of the most sensitive particle detectors ever devised. These detectors are marvels of engineering and physics, designed to register the incredibly rare interactions that might occur when a dark matter particle collides with the nucleus of an ordinary atom. The detectors themselves are often made of extremely pure materials, sometimes purer than anything found naturally on Earth, to minimize any possible source of background interference. Some experiments use tanks of liquid xenon, a noble gas that has been cooled to extremely low temperatures and compressed into a liquid state. Xenon is particularly useful for dark matter detection because its atomic nuclei are heavy enough to provide a reasonable target for dark matter particles. Yet the liquid is transparent enough that sensitive instruments can detect the tiny flashes of light that might be produced when a dark matter particle strikes a xenon nucleus. Other experiments employ crystals of silicon or germanium, cooled to temperatures just a few degrees above absolute zero. At these incredibly low temperatures, any energy deposited by a colliding dark matter particle would heat the crystal by a measurable amount, creating a signal that can be detected by sensitive thermometers attached to the crystal surface. The technical challenges involved in these experiments are staggering. The detectors must be sensitive enough to register the energy deposited by a single particle collision, yet stable enough to operate continuously for months or years without being disturbed by vibrations, temperature fluctuations, or electromagnetic interference from the outside world. The detectors are typically surrounded by multiple layers of shielding made from carefully selected materials. Lead blocks absorb gamma rays from natural radioactivity in the surrounding rock. Polyethylene plastic slows down neutrons that might mimic dark matter signals. Copper chambers provide electromagnetic shielding and are made from copper that was smelted before 1945. Ensuring that it contains no radioactive isotopes created by nuclear weapons testing. Despite these extraordinary precautions, the experiments must still contend with irreducible sources of background that cannot be completely eliminated. Natural radioactivity in the detector materials themselves, cosmic ray muons that occasionally penetrate even the deepest underground laboratories, and neutrons produced by radioactive decay all contribute to a steady stream of false signals that must be carefully distinguished from genuine dark matter interactions. The data analysis required to identify potential dark matter signals among this background is extraordinarily sophisticated, employing advanced statistical techniques and machine learning algorithms to search for subtle patterns that might indicate the presence of dark matter. Teams of physicists spend years analyzing each dataset, checking and double-checking every aspect of their analysis to ensure that any claimed detection is genuine. After decades of increasingly sensitive searches, these underground experiments have yet to make a confirmed detection of dark matter particles. However, they have not failed entirely. Instead, they have succeeded in placing increasingly stringent limits on how strongly dark matter can interact with ordinary matter, ruling out many theoretical models and forcing scientists to consider more exotic possibilities for dark matter's nature. The second major approach to dark matter detection involves using particle accelerators to create dark matter particles artificially in high-energy collisions between ordinary particles. The most powerful of these machines is the Large Hadron Collider, built in a circular tunnel 27 kilometers in circumference beneath the border between France and Switzerland. The Large Hadron Collider accelerates protons to nearly the speed of light, and then smashes them together with energies equivalent to those that existed in the first trillionth of a second after the Big Bang. In these violent collisions, the kinetic energy of the colliding protons is converted into new particles, according to Einstein's famous equation relating mass and energy. If dark matter particles can be created in such collisions, they would immediately escape the detector without leaving any direct trace, much like neutrinos do in similar experiments. However, the missing energy and momentum carried away by these invisible particles can be inferred from careful analysis of all the other particles produced in the collision. The signature of dark matter production would appear as an imbalance in the total energy and momentum of all the visible particles created in the collision. By the fundamental conservation laws of physics, energy and momentum cannot simply disappear, so any missing energy must have been carried away by invisible particles, potentially including dark matter. The challenge lies in distinguishing dark matter production from the many other processes that can create missing energy signatures. Neutrinos, which interact so weakly that they pass through the entire Earth without being stopped, routinely carry away energy from particle collisions. Detector malfunctions or inefficiencies can also create apparent missing energy when particles escape detection. Despite analyzing billions of particle collisions over more than a decade of operation, the Large Hadron Collider has not yet found convincing evidence for dark matter production. However, like the underground detection experiments, these searches have provided valuable constraints on the properties that dark matter particles can have, eliminating many theoretical possibilities and guiding the development of new models. The third approach to dark matter detection takes advantage of the possibility that dark matter particles might occasionally annihilate with each other, converting their mass back into energy in the form of high-energy photons, electrons, positrons, or other ordinary particles that can be detected by space-based telescopes. This indirect detection strategy focuses on regions of space where dark matter is expected to be highly concentrated, such as the centers of galaxies or the dense cores of galaxy clusters. In these environments, dark matter particles would be packed closely enough together that occasional annihilation events might produce detectable signals. Space-based gamma-ray telescopes, like the Fermi Gamma-Ray Space Telescope, continuously scan the sky, looking for high-energy photons that might be produced by dark matter annihilation. These instruments must distinguish potential dark matter signals from the many other astrophysical sources of gamma rays, including pulsars, black holes, and supernova remnants. The most promising targets for indirect detection include dwarf satellite galaxies that orbit the Milky Way. These small galaxies are thought to be dominated by dark matter, with very few ordinary stars to complicate the analysis. Any gamma-ray emission from these galaxies that cannot be explained by known astrophysical processes might be evidence of dark matter annihilation. Other space-based instruments search for the antimatter particles that might be produced when dark matter annihilates. The Alpha Magnetic Spectrometer, mounted on the International Space Station, measures the flux of cosmic ray positrons and antiprotons with unprecedented precision, looking for excess antimatter that might indicate dark matter annihilation in the galactic halo. Ground-based telescopes also contribute to the indirect search by detecting the very high-energy gamma rays that might be produced in dark matter-rich environments. Arrays of Cherenkov telescopes, which detect the brief flashes of blue light produced when high-energy gamma rays interact with Earth's atmosphere, provide another window into potential dark matter annihilation signals. The search for dark matter has also driven the development of entirely new detection technologies and experimental techniques. Scientists have proposed using quantum sensors, superconducting devices, and even tabletop experiments that might be sensitive to certain types of dark matter interactions that would be missed by conventional approaches. Some experiments search for axion dark matter by looking for the weak conversion of axions into photons in strong magnetic fields. These experiments typically employ powerful electromagnets and sensitive microwave receivers, attempting to detect the faint radio signals that would be produced if actions in the galactic halo were converted into photons as they passed through the magnetic field. Other proposed experiments would search for dark matter interactions with atomic clocks, GPS satellites, or gravitational wave detectors. These approaches take advantage of the fact that different types of dark matter might interact with matter in ways that affect the passage of time, the propagation of light, or the curvature of space-time itself. The global nature of the dark matter search has fostered unprecedented international collaboration among scientists from dozens of countries. Experimental teams routinely share data, coordinate their search strategies, and combine results from multiple experiments to maximize their collective sensitivity to potential dark matter signals. This collaborative approach has proven essential because the signals that dark matter experiments are searching for are so weak and subtle that extraordinary care must be taken to avoid false discoveries. Multiple independent experiments must confirm any claimed detection before the scientific community will accept it as genuine evidence for dark matter. The search has also driven innovation in data analysis techniques, statistical methods, and computational approaches to handling vast datasets. Machine learning algorithms originally developed for dark matter searches have found applications in other fields, from medical imaging to financial analysis, demonstrating the broader technological benefits of fundamental research. Despite decades of intensive searching, using increasingly sophisticated techniques and ever more sensitive instruments, dark matter continues to evade direct detection. This persistent elusiveness has led some scientists to question whether dark matter consists of particles at all, or whether the phenomena attributed to dark matter might require modifications to our understanding of gravity itself. However, the vast majority of scientists remain convinced that dark matter particles exist and that improved experiments will eventually succeed in detecting them directly. Each new generation of experiments pushes the sensitivity limits further, probing interaction strengths that are orders of magnitude weaker than what previous generations could achieve. The hunt for dark matter represents more than just an attempt to solve a single scientific puzzle. It embodies humanity's relentless drive to understand the fundamental nature of reality, even when that reality proves to be far stranger and more elusive than we ever imagined. Every underground laboratory, every particle collision, every gamma-ray observation brings us one step closer to finally grasping the true nature of the invisible universe that surrounds us. The search continues in the depths of our planet and across the cosmos, driven by the conviction that the universe's greatest secrets are waiting to be discovered by those bold enough to look for them in the darkness between the stars. Just as scientists were beginning to grasp the profound implications of dark matter's dominance over the universe, an even more startling discovery was about to revolutionize our understanding of cosmic evolution. In the late 1990s, two independent teams of astronomers set out to measure how the expansion of the universe was slowing down over time. What they found instead was so unexpected, so contrary to all theoretical predictions, that it forced humanity to confront the existence of an entirely new and even more mysterious component of the cosmos. The story of dark energy's discovery begins with a simple yet profound question that had puzzled cosmologists for decades. Ever since Edwin Hubble's groundbreaking observations in the 1920s revealed that the universe was expanding, scientists had assumed that this expansion must be gradually slowing down due to the gravitational attraction of all the matter contained within it. This assumption seemed entirely reasonable and was supported by the best theoretical understanding of cosmic evolution. Just as a ball thrown upward from Earth's surface gradually slows down due to gravitational pull, the expansion of the universe should decelerate as gravity works to pull all matter back together. The only question was whether the universe contained enough matter to eventually halt the expansion entirely, or whether it would continue expanding forever at an ever-decreasing rate. Two competing teams of astronomers, driven by the desire to settle this fundamental question about the universe's ultimate fate, embarked on ambitious, observational campaigns to measure the expansion history of the cosmos with unprecedented precision. The Supernova Cosmology Project, led by Saul Perlmutter at Lawrence Berkeley National Laboratory, and the High Z Supernova Search Team, led by Brian Schmidt and Adam Rees, both chose to use Type Ia supernovae as cosmic standard candles to probe the expansion rate at different epochs in cosmic history. Type Ia supernovae represent one of nature's most remarkable astronomical phenomena. These catastrophic explosions occur when a white dwarf star, the dense remnant of a sun-like star that has exhausted its nuclear fuel, accumulates material from a companion star until it reaches a critical mass threshold. At this precise moment, the white dwarf undergoes a thermonuclear explosion so violent that it briefly outshines an entire galaxy containing billions of stars. What makes Type Ia supernovae invaluable for cosmological studies is their extraordinary consistency. Because the explosion always occurs when the white dwarf reaches the same critical mass, roughly 1.4 times the mass of our Sun, these supernovae always release approximately the same amount of energy and reach nearly identical peak brightness. This consistency makes them perfect cosmic lighthouses, allowing astronomers to determine their distances by comparing their observed brightness to their known intrinsic luminosity. By observing supernovae at various distances, and therefore at different times in the past due to the finite speed of light, astronomers could map out how the expansion rate of the universe had changed over cosmic time. Supernovae that exploded billions of years ago would reveal the expansion rate when the universe was much younger, while more recent explosions would show how fast the universe is expanding today. The observational campaign required by this ambitious project was staggering in its scope and technical demands. Both teams needed to discover supernovae when they were just beginning to brighten, before they reached peak luminosity, in order to obtain complete light curves showing how their brightness changed over time. This meant repeatedly photographing the same patches of sky night after night, comparing new images to reference photographs to identify the sudden appearance of new stellar objects. Once a supernova was discovered, teams of astronomers around the world would coordinate their observations, using some of the largest and most sophisticated telescopes on Earth to measure the precise brightness and spectral characteristics of each explosion. The supernovae being studied were so distant that even the most powerful telescopes could barely detect them, requiring hours of exposure time and careful analysis to extract reliable measurements. The data analysis process was equally challenging and required developing entirely new techniques for handling the vast amounts of observational data. Astronomers had to account for countless sources of systematic error, from atmospheric effects that could alter the apparent brightness of distant objects, to the possibility that supernovae in the early universe might have been intrinsically different from those observed today. By the late 1990s, both teams had accumulated enough high-quality supernova observations to begin drawing conclusions about the expansion history of the universe. The results that emerged from their careful analysis were completely unexpected and profoundly disturbing to the established cosmological worldview. Instead of finding evidence that the expansion of the universe was slowing down, as every theoretical model predicted, both teams discovered that the expansion was actually accelerating. The universe was not only continuing to expand, but it was expanding faster and faster with each passing moment. Distant supernovae appeared fainter than they should have if the universe were decelerating, indicating that they were farther away than expected for their observed redshift. The implications of this discovery were staggering and difficult to accept. If the expansion of the universe was accelerating, then some unknown force must be driving this acceleration, working against the gravitational attraction of all matter in the universe. This force would need to be not only present throughout all of space, but actually dominant over gravity on the largest cosmic scales. The initial reaction from the broader scientific community was one of skepticism and disbelief. The results seemed to contradict everything that physicists thought they understood about the fundamental forces of nature. Gravity was supposed to be attractive, always working to pull matter together and slow down the cosmic expansion. What could possibly be powerful enough to overcome gravity throughout the entire universe? Both research teams spent months double-checking their analysis, looking for any possible source of error that could explain away the surprising result. They considered whether dust in distant galaxies might be dimming the supernovae and making them appear more distant than they actually were. They investigated whether the supernovae themselves might have evolved over cosmic time, becoming intrinsically dimmer in the past compared to those observed today. Every possible source of systematic error was carefully examined and ruled out. The teams even analyzed each other's data using independent methods, arriving at the same startling conclusion. The acceleration of the universe's expansion was real, reproducible, and undeniable. As word of the discovery spread through the astronomical community, it triggered a revolution in cosmological thinking that continues to this day. The existence of cosmic acceleration implied the presence of a new component of the universe that had never been detected or predicted by any theory. This mysterious component would need to possess properties unlike anything known to physics. Unlike ordinary matter and even dark matter, which exert attractive gravitational forces, this new component would need to have a repulsive gravitational effect, pushing space itself apart with ever-increasing vigor. The energy density of this component would need to remain constant even as the universe expanded, so that its repulsive effect would grow stronger as ordinary matter became more diluted. Scientists gave this mysterious new component the name dark energy, reflecting both its invisible nature and its profound ignorance about its fundamental properties. The name was chosen to parallel dark matter, but dark energy would prove to be an even deeper mystery, challenging physicists' understanding of the most basic concepts of space, time, and energy. Follow-up observations using improved techniques and larger samples of supernovae confirmed the reality of cosmic acceleration beyond any reasonable doubt. The Hubble Space Telescope, with its ability to observe supernovae free from atmospheric interference, provided even more precise measurements that solidified the case for dark energy. Other independent lines of evidence soon emerged to support the supernova results. Observations of the cosmic microwave background radiation, the afterglow of the Big Bang itself, revealed subtle patterns that were consistent with a universe dominated by dark energy. Studies of large-scale structure, mapping the distribution of galaxies across cosmic time, also supported the existence of a repulsive component, driving accelerated expansion. The discovery of dark energy earned Saul Perlmutter, Brian Schmidt, and Adam Riess the 2011 Nobel Prize in Physics, recognizing their revolutionary contribution to our understanding of the universe. Their work had revealed that not only was most of the matter in the universe invisible dark matter, but that space itself was dominated by an even more mysterious form of energy that was driving the cosmos apart. The confirmation of cosmic acceleration marked a turning point in cosmology, forcing scientists to confront the humbling realization that they understood less about the universe than they had previously believed. Dark energy appeared to make up roughly 68% of the total energy density of the universe, dwarfing both ordinary matter and dark matter in its cosmic significance. Yet, despite more than 2 decades of intensive research since its discovery, dark energy remains as mysterious today as it was when those first supernova observations revealed its existence. Scientists have proposed numerous theories to explain its nature, from modifications to Einstein's theory of gravity to exotic quantum phenomena involving the vacuum of space itself. The search for understanding dark energy has become one of the most active areas of research in modern physics and astronomy, driving the construction of new telescopes, the development of innovative observational techniques, and the formulation of bold new theories about the fundamental nature of space and time. What we once thought was slowing down was, in fact, speeding up. A new mystery had emerged from the distant stars, one that would prove even more challenging to solve than the puzzle of dark matter. The universe, it seemed, was not only stranger than we had imagined, but stranger than we had thought it possible to imagine. The discovery of cosmic acceleration left scientists grappling with a phenomenon that seemed to defy every intuition about how the universe should behave. Dark energy, the mysterious force driving this acceleration, possesses properties so strange and counterintuitive that it challenges our most fundamental understanding of space, time, and the nature of existence itself. Unlike dark matter, which at least behaves somewhat like ordinary matter in its gravitational effects, dark energy appears to operate according to rules that seem almost magical in their violation of everyday experience. To understand just how bizarre dark energy truly is, consider what we know about its most basic properties. Dark energy does not clump together like ordinary matter, or even dark matter. Instead, it appears to be perfectly smooth and uniform throughout all of space, maintaining the same density everywhere, from the vast emptiness between galaxy clusters to the densest regions within galaxies themselves. This uniformity is so perfect that no variation in dark energy density has ever been detected, despite increasingly sensitive observations. Even more puzzling is dark energy's behavior as the universe expands. When ordinary matter spreads out over larger volumes of space, its density decreases proportionally. If you take a box of gas and double its volume, the density of gas inside becomes half what it was before. Dark matter behaves similarly, becoming more diluted as space expands and galaxies move farther apart. Dark energy, however, appears to violate this fundamental expectation. As the universe expands and volumes increase, the density of dark energy remains exactly the same. This means that the total amount of dark energy in any given region of space actually increases as that region expands, as if the expansion of space itself is creating new dark energy from nothing. This property has profound implications for the future evolution of the universe. While matter and radiation become increasingly diluted as cosmic expansion continues, dark energy maintains its density and therefore its influence. Over time, dark energy becomes more and more dominant compared to all forms of matter, driving the acceleration of expansion to ever greater extremes. The repulsive nature of dark energy's gravitational effect represents another fundamental departure from everything we know about matter and energy. In Einstein's theory of general relativity, the curvature of space-time that we experience as gravity depends not just on the density of matter and energy, but also on the pressure exerted by that matter and energy. For ordinary matter and radiation, this pressure contribution reinforces the attractive nature of gravity, making the gravitational pull even stronger. Dark energy appears to exert a negative pressure, meaning that it pulls inward on itself while simultaneously pushing outward on everything around it. This negative pressure is so strong that it more than compensates for the attractive effect of dark energy's positive energy density, resulting in a net repulsive gravitational effect that drives cosmic acceleration. The magnitude of this negative pressure is precisely what determines the strength of dark energy's repulsive effect. Theoretical calculations suggest that for dark energy to produce the observed acceleration, its negative pressure must be exactly equal in magnitude to its positive energy density. This precise balance seems remarkably special and has led some scientists to wonder whether there might be a deeper principle or symmetry that requires this relationship. The energy scale associated with dark energy presents yet another puzzle that highlights how little we understand about its true nature. When physicists calculate the energy density of dark energy based on astronomical observations, they find that it corresponds to an incredibly tiny amount of energy per unit volume of space. A cubic meter of empty space contains dark energy equivalent to only a few hydrogen atoms worth of mass energy. This energy density seems impossibly small by the standards of particle physics and quantum mechanics. Theoretical calculations of the energy that should be present in empty space due to quantum fluctuations predict values that are larger than the observed dark energy density by factors of 10 to the power of 60 or more. This represents perhaps the worst disagreement between theory and observation in the entire history of physics. The fact that dark energy's density is so much smaller than theoretical expectations has led to what physicists call the cosmological constant problem. Why should the energy of empty space be so incredibly tiny rather than the enormous value that quantum mechanics seems to predict? This question touches on some of the deepest issues in theoretical physics and may require completely new insights into the nature of space, time, and quantum mechanics to resolve. Despite these puzzles, scientists have proposed several theoretical frameworks that attempt to explain dark energy's properties and behavior. The simplest possibility is that dark energy represents the cosmological constant that Einstein originally introduced into his equations of general relativity. Einstein added this constant to allow for static universe solutions, but later called it his greatest blunder when Hubble discovered cosmic expansion. The cosmological constant can be interpreted as the energy density of empty space itself, arising from quantum fluctuations in the vacuum. In this view, every point in space contains a fundamental background energy that exerts negative pressure and drives cosmic acceleration. The cosmological constant would be truly constant throughout space and time, never changing as the universe evolves. While the cosmological constant provides the simplest explanation for dark energy, it suffers from the magnitude problem mentioned earlier. There is no known mechanism that could suppress the vacuum energy to the incredibly small value required to match observations. This has led many physicists to explore alternative explanations that might naturally produce the right amount of dark energy. One popular alternative is called quintessence, named after the fifth element that ancient philosophers believed filled the heavens beyond the four earthly elements of earth, air, fire, and water. Quintessence models propose that dark energy arises from a new type of field that permeates all of space, similar to the electromagnetic field, but with very different properties. Unlike the cosmological constant, quintessence fields would be dynamic, capable of changing their energy density and pressure over time. This evolution could potentially explain why dark energy has the particular value we observe today, perhaps as the result of the field rolling down from higher energy states in the past toward lower energy states in the future. Different quintessence models predict different behaviors for how dark energy might evolve over cosmic time. Some models suggest that dark energy could eventually decay away, allowing gravity to regain dominance and potentially leading to a future collapse of the universe. Other models predict that dark energy could grow stronger over time, leading to increasingly rapid acceleration that might eventually tear apart all bound structures in the cosmos. More exotic theoretical possibilities include phantom dark energy, which would have negative energy density rather than positive energy density. Phantom dark energy would lead to a dramatic future evolution called the Big Rip, in which the acceleration of expansion becomes so extreme that it eventually overcomes all other forces, tearing apart galaxies, stars, atoms, and even the fabric of space-time itself. Other theories propose that what we interpret as dark energy might actually arise from modifications to Einstein's theory of gravity on the largest cosmic scales. Just as Newton's law of gravity required modification when applied to very high speeds or strong gravitational fields, Einstein's general relativity might need modification when applied to the entire observable universe. These modified gravity theories attempt to produce cosmic acceleration without invoking any new form of energy, instead proposing that gravity itself behaves differently on cosmic scales than it does in the solar system, where it has been most precisely tested. Some of these theories predict subtle differences in how cosmic acceleration should depend on the scale and epoch being observed, providing potential ways to test whether dark energy truly exists or whether gravity itself needs revision. The possibility that dark energy arises from extra-spatial dimensions beyond the three we directly experience represents another frontier in theoretical physics. In these models, gravity might leak into higher dimensional spaces on very large scales, weakening its attractive effect and creating an apparent repulsive force that mimics the effects of dark energy. String theory, which attempts to unify all fundamental forces by treating particles as vibrating strings rather than point objects, predicts the existence of many additional spatial dimensions beyond the three we observe. If these extra dimensions have the right properties, they could potentially explain both dark energy and dark matter as manifestations of ordinary physics operating in a higher dimensional space. The search for a deeper understanding of dark energy has driven the construction of increasingly ambitious, observational projects designed to map cosmic acceleration with unprecedented precision. Future space-based telescopes will observe millions of supernovae and other distance indicators to trace the expansion history of the universe in exquisite detail. Large ground-based surveys are mapping the positions and properties of billions of galaxies to study how cosmic structure has evolved under the influence of dark energy. These observations can reveal subtle effects of dark energy on the growth of galaxy clusters and the distribution of matter on the largest observable scales. The study of gravitational waves, ripples in space-time itself, detected by facilities like LIGO and Virgo, offers yet another window into dark energy's properties. As gravitational waves travel across cosmic distances, they carry information about the expansion history of the universe and the nature of space-time that could provide new clues about dark energy's true nature. Despite more than 2 decades of intensive research since its discovery, dark energy remains one of the deepest mysteries in all of science. Its properties seem to require either entirely new physics beyond our current understanding or remarkable fine-tuning of known physics to produce exactly the right conditions for cosmic acceleration. The implications of dark energy extend far beyond academic cosmology. Its existence suggests that our universe may be heading toward a future very different from what earlier generations of scientists imagined. Instead of eventually contracting under gravity's pull, or expanding to a cold, dark but stable final state, the universe appears destined for eternal acceleration that will eventually carry distant galaxies beyond the reach of observation. Understanding dark energy may require revolutionary advances in our understanding of space, time, matter, and energy themselves. The solution to this cosmic puzzle could unlock new technologies, reveal new principles of physics, and fundamentally change humanity's perspective on our place in an accelerating universe. Dark energy is not just a force that drives cosmic expansion, but rather the engine behind the universe's evolution toward an uncertain and potentially dramatic future. Its true nature remains hidden behind a veil of mystery that continues to challenge the brightest minds in physics and astronomy, promising discoveries that could transform our understanding of reality itself. To understand where dark matter and dark energy came from, we must journey back to the very beginning of everything, to the first moments when the universe itself was born in an event so violent and transformative that it created not only all matter and energy, but space and time themselves. The origins of these mysterious forces are intimately connected to the most fundamental processes that shaped our cosmos during its earliest and most dramatic epochs. The story begins 13.8 billion years ago, in an infinitesimal point containing all the matter, energy, and potential that would ever exist. This singularity, smaller than the smallest particle yet containing everything, suddenly began expanding in an event we call the Big Bang. But this was not an explosion in the conventional sense, with matter flying outward through existing space. Instead, space itself came into being and began expanding, carrying matter and energy along with it. In the first tiny fraction of a second after the Big Bang, the universe underwent a period of exponential expansion called cosmic inflation. During this brief but crucial epoch, the universe grew from subatomic scales to macroscopic sizes faster than the speed of light, stretching quantum fluctuations in the fabric of space-time itself into the seeds that would eventually become galaxies and galaxy clusters. It was during these earliest moments that the fundamental components of our universe may have been established. The extreme temperatures and energies present immediately after the Big Bang created conditions unlike anything that exists today, allowing processes to occur that would be impossible under normal circumstances. In this primordial furnace, the basic building blocks of both ordinary matter and dark matter likely came into existence. The creation of dark matter particles in the early universe would have depended on the specific properties of these hypothetical particles and the forces through which they interact. If dark matter consists of weakly interacting massive particles, as many theories suggest, these particles would have been produced abundantly during the first moments when the universe was hot enough for particle-antiparticle pairs to be created from pure energy. As the universe expanded and cooled, the production of new particle pairs would have eventually ceased, and most existing particles would have annihilated with their antiparticles, converting their mass back into energy. However, if the annihilation process was not perfectly efficient, a small residual population of dark matter particles could have survived this cosmic winnowing process. The amount of dark matter that survived to the present day would have been determined by the precise balance between the rate at which dark matter particles were created, the rate at which they annihilated, and the rate at which the universe was expanding and cooling. This delicate balance had to be just right to produce the amount of dark matter we observe today, neither so much that it would have caused the universe to collapse immediately, nor so little that it could not provide the gravitational framework for galaxy formation. Alternative theories propose that dark matter particles were created through entirely different mechanisms during the early universe. Some models suggest that dark matter could have been produced during phase transitions in the fundamental forces, similar to how water transforms from liquid to ice when cooled below the freezing point. During such cosmic phase transitions, enormous amounts of energy could have been converted into dark matter particles through processes that have no analog in today's much cooler universe. Other theories propose that dark matter originated even earlier, during the cosmic inflation period itself. Quantum fluctuations in hypothetical fields during inflation could have led to the production of dark matter particles with properties that would make them invisible to electromagnetic radiation, but still subject to gravitational attraction. These primordial dark matter particles would have been spread throughout the expanding universe from the very beginning, providing the foundation for all subsequent structure formation. The origin of dark energy presents an even greater challenge to our understanding of fundamental physics. Unlike dark matter, which at least behaves somewhat like ordinary matter in its gravitational effects, dark energy appears to arise from the very fabric of space itself. Its origin may be connected to the most basic properties of quantum mechanics and the nature of empty space. One possibility is that dark energy represents the zero-point energy of quantum fields that permeate all of space. According to quantum mechanics, even completely empty space is never truly empty, but instead seethes with virtual particles that constantly appear and disappear on timescales so brief that they cannot be directly observed. These quantum fluctuations contribute an energy density to empty space that could, in principle, act like a cosmological constant, driving cosmic acceleration. However, when physicists attempt to calculate the magnitude of this vacuum energy using known principles of quantum field theory, they arrive at values that are incomprehensibly larger than the observed dark energy density. This suggests either that our understanding of quantum mechanics is fundamentally incomplete, or that some unknown mechanism suppresses the vacuum energy to the incredibly tiny value required to match observations. Another possibility is that dark energy arose during a phase transition in the early universe, similar to how dark matter might have been created, but occurring much later in cosmic history. In this scenario, a field that was initially at a high energy state during the early universe could have undergone a transition to a lower energy state, leaving behind a residual energy density that we observe today as dark energy. The timing of such a phase transition would be crucial. If it occurred too early, the resulting dark energy would have prevented the formation of galaxies and stars. If it occurred too late, we would not observe the cosmic acceleration that characterizes our current epoch. The phase transition would need to have occurred at just the right time in cosmic history to produce the dark energy we observe today. Some theories propose that dark energy is not constant, but instead evolves over time as the universe expands and cools. In these models, dark energy could have had different values in the past and might continue to change in the future. The field responsible for dark energy could be slowly rolling from higher energy states toward lower energy states, with the current acceleration representing just one phase in this cosmic evolution. The connection between dark energy and cosmic inflation represents another intriguing possibility. The same type of field that drove the exponential expansion during inflation could have been reactivated much later in cosmic history, producing the accelerated expansion we observe today. This would provide a unified explanation for two of the most dramatic epochs in cosmic evolution, linking the earliest moments of the Big Bang to the current accelerating expansion. The anthropic principle offers yet another perspective on the origins of dark matter and dark energy. This controversial idea suggests that the properties of dark matter and dark energy in our universe may be determined by the requirement that they allow for the existence of observers like ourselves. In this view, universes with very different amounts of dark matter or dark energy would not develop the complex structures necessary for life. So we naturally find ourselves in a universe where these components have values compatible with our existence. If the anthropic principle is correct, then the origins of dark matter and dark energy might not reflect fundamental physical laws, but rather a selection effect among many possible universes. This interpretation is supported by some theories of cosmic inflation that predict the creation of multiple universes with different physical properties, only some of which would be suitable for the development of life and consciousness. The relationship between dark matter and dark energy during the universe's early history remains one of the most profound mysteries in cosmology. These two components appear to be completely unrelated, interacting only through gravity and evolving according to very different rules. Yet both are essential for the universe we observe today, suggesting that their origins might be connected in ways we do not yet understand. Recent theoretical work has explored the possibility that dark matter and dark energy could be different manifestations of the same underlying field or force. In these unified models, the same mechanism that created dark matter in the early universe could also be responsible for the dark energy we observe today. Such theories would provide an elegant explanation for why both dark components are necessary and why they have the particular properties we observe. The study of cosmic microwave background radiation, the afterglow of the Big Bang that still pervades the universe today, provides crucial clues about the early history of dark matter and dark energy. Subtle patterns in this radiation preserve information about the state of the universe when it was only 380,000 years old, including the distribution of dark matter and the potential effects of dark energy. Future observations of the cosmic microwave background with increasingly sensitive instruments may reveal new details about how dark matter and dark energy behaved during the universe's infancy. These observations could help distinguish between different theoretical models and provide new insights into the fundamental processes that gave rise to these mysterious components. The search for the origins of dark matter and dark energy has driven theoretical physicists to explore some of the most exotic and speculative ideas in modern science. String theory, extra dimensions, parallel universes, and modifications to the basic laws of physics all offer potential explanations for how these components could have arisen from the primordial conditions of the early universe. Laboratory experiments designed to recreate the extreme conditions present during the Big Bang may eventually provide direct evidence about the mechanisms that created dark matter and dark energy. Particle accelerators like the Large Hadron Collider can probe energy scales that existed during the first moments after the Big Bang, potentially revealing new particles and forces that played crucial roles in the early universe. The origins of dark matter and dark energy represent some of the deepest questions we can ask about the nature of existence itself. Understanding how these components came to dominate our universe requires us to probe the very foundations of space, time, matter, and energy. The answers may revolutionize our understanding of physics and cosmology, revealing new principles that govern the behavior of the cosmos on its largest scales. As we continue to search for these answers, we are essentially trying to read the biography of the universe itself, deciphering the cosmic story written in the distribution of galaxies, the properties of distant supernovae, and the subtle fluctuations in the cosmic microwave background. Each new observation brings us closer to understanding the remarkable chain of events that led from the Big Bang to the complex, accelerating universe we inhabit today. To understand where dark matter and dark energy came from, we must look back to the beginning, to the very first moments of the universe, when all possibilities were open and the fundamental character of reality was being established for all time. In the first few 100 million years after the Big Bang, the universe was a very different place than the cosmos we observe today. There were no stars yet shining in the darkness, no galaxies spinning majestically through space, and no planets orbiting distant suns. Instead, the universe was filled with a nearly uniform sea of hydrogen and helium gas, slowly cooling as space itself continued to expand from the initial moment of creation. Yet even in this seemingly empty and featureless epoch, dark matter and dark energy were already playing crucial roles in shaping the destiny of everything that would ever exist. Though invisible to any hypothetical observer who might have been present during those ancient times, these mysterious forces were quietly orchestrating the cosmic symphony that would eventually give birth to all the complexity and beauty we see around us today. Dark matter, having been created during the first moments after the Big Bang, was already beginning to assert its gravitational influence throughout the expanding universe. Unlike ordinary matter, which was still too hot and energetic to form stable structures, dark matter was cool enough to begin clumping together under its own gravitational attraction, creating the first concentrations of mass in an otherwise smooth cosmos. These early dark matter clumps were incredibly subtle, representing variations in density of only a few parts in 100,000 compared to the average density of the universe. To put this in perspective, imagine trying to detect hills and valleys on a perfectly flat plain where the highest peaks rose only a few inches above the surrounding landscape. Yet these tiny fluctuations contained the seeds of every galaxy, star, and planet that would ever form. The growth of these dark matter concentrations was a gradual process that unfolded over millions of years. Regions with slightly higher than average dark matter density would exert a slightly stronger gravitational pull on surrounding matter, attracting additional dark matter and causing the overdensity to grow slowly but inexorably. Meanwhile, regions with lower than average density would lose matter to their denser neighbors, becoming increasingly empty as time passed. This process of gravitational amplification meant that the rich grew richer while the poor grew poorer, leading to an increasingly lumpy distribution of dark matter throughout the universe. What began as tiny ripples in the cosmic density field gradually evolved into a vast network of dark matter filaments, nodes, and voids that would provide the invisible scaffolding for all future cosmic structure. The ordinary matter that would eventually form stars and galaxies was initially unable to participate in this early phase of structure formation. In the first few 100,000 years after the Big Bang, the universe was so hot that electrons could not remain bound to atomic nuclei, creating a plasma of free charged particles that interacted strongly with the radiation that filled all of space. This coupling between matter and radiation prevented ordinary matter from clumping together as effectively as dark matter. Any attempt by ordinary matter to form concentrations would be disrupted by the pressure of the intense radiation field, which would push the charged particles apart and smooth out any developing structure. Dark matter, however, was immune to these disruptive effects. Because dark matter particles do not carry electric charge, they do not interact with electromagnetic radiation and were therefore free to respond only to gravitational forces. This gave dark matter a crucial head start in the race to form cosmic structures, allowing it to begin building the framework that would eventually guide the assembly of everything we see today. The situation changed dramatically when the universe was approximately 380,000 years old, during an epoch cosmologists call recombination. By this time, the universe had expanded and cooled enough that electrons could finally combine with protons to form neutral hydrogen atoms. This transition marked the end of the cosmic dark age and the beginning of a new era in cosmic evolution. With the formation of neutral atoms, ordinary matter was suddenly freed from its coupling to radiation. The electromagnetic forces that had previously prevented ordinary matter from clumping together were no longer effective, allowing hydrogen and helium gas to begin falling into the gravitational wells that dark matter had already carved out in the cosmic landscape. This moment represents one of the most important transitions in the entire history of the universe. For the first time, ordinary matter could begin to trace the invisible dark matter structures that had been growing in the shadows for hundreds of thousands of years. The cosmic web that dark matter had woven in the darkness was finally ready to be illuminated by the first generation of stars and galaxies. The process by which ordinary matter fell into dark matter halos was not instantaneous but unfolded over millions of additional years. As hydrogen and helium gas streamed into the deepest gravitational wells, it began to heat up due to compression and gravitational compression, eventually reaching temperatures and densities sufficient for the first stars to ignite their nuclear fires. These first stars were very different from the Sun and other stars we see today. Because the universe contained only hydrogen and helium at this time, with no heavier elements yet created by stellar nucleosynthesis, the first stars were composed entirely of the lightest elements. This simple composition allowed them to grow to enormous sizes, often hundreds of times more massive than our Sun. These primordial giants burned their nuclear fuel at prodigious rates, shining with the brilliance of millions of ordinary stars. However, their massive size also meant that they had very short lifespans, burning out and exploding as supernovae after only a few million years. When they died, they scattered the first heavy elements throughout the surrounding space, enriching the universe with carbon, oxygen, silicon, iron, and other elements essential for the formation of planets and life. The explosions of these first stars also had profound effects on the surrounding dark matter and gas. The enormous energies released by these supernovae could push ordinary matter out of small dark matter halos, preventing the formation of additional stars in those regions. This feedback mechanism created a complex interplay between star formation and dark matter that continues to influence cosmic evolution today. Meanwhile, dark energy was also beginning to make its presence felt during this early epoch, though its effects were much more subtle than those of dark matter. In the first few billion years after the Big Bang, the universe was much denser than it is today, and the attractive gravitational effects of matter dominated over the repulsive effects of dark energy. However, as the universe continued to expand and ordinary matter and dark matter became increasingly diluted, the influence of dark energy gradually grew stronger. Unlike matter, which becomes less dense as the universe expands, dark energy maintains a constant density throughout cosmic time. This means that dark energy's share of the total energy budget of the universe has been steadily increasing since the Big Bang. The transition from a matter-dominated universe to a dark energy-dominated universe occurred relatively recently in cosmic history, approximately 5 billion years ago. Before this transition, the expansion of the universe was indeed slowing down due to the gravitational attraction of matter, just as scientists had expected before the discovery of cosmic acceleration. The timing of this transition has profound implications for the development of cosmic structure. If dark energy had become dominant earlier in cosmic history, its repulsive effects would have prevented the formation of galaxies and stars. If it had become dominant much later, or not at all, the universe might have eventually collapsed back in on itself in a big crunch. The fact that dark energy became dominant at just the right time to allow for billions of years of galaxy and star formation, yet not so late as to prevent cosmic acceleration, seems remarkably fortunate from the perspective of life and complexity in the universe. This apparent fine-tuning has led some scientists to wonder whether there might be deeper principles at work that require dark energy to have its observed properties. The early universe also witnessed the formation of the first galaxy clusters, vast assemblages of dark matter, gas, and eventually galaxies that represent the largest gravitationally bound structures in the cosmos. These clusters formed at the intersections of dark matter filaments, where multiple streams of matter converge to create the deepest gravitational wells in the universe. The formation of galaxy clusters was a hierarchical process, with smaller structures merging together to build progressively larger systems over cosmic time. This bottom-up assembly process, driven by the gravitational attraction of dark matter, continues today as we observe clusters still growing through the accretion of smaller galaxy groups and individual galaxies. Computer simulations of cosmic evolution have revealed the intricate dance between dark matter and ordinary matter during these early epochs. These simulations show how dark matter halos of different masses formed at different times, with the smallest structures forming first and larger structures assembling later through mergers and accretion. The simulations also reveal the crucial role that dark energy played in determining the overall pace of structure formation. By gradually slowing down the growth of cosmic structures as it became more dominant over time, dark energy helped determine when the most massive galaxy clusters would form and how much time would be available for stars and galaxies to develop. The relationship between dark matter, dark energy, and ordinary matter during the universe's youth established patterns that persist to this day. Dark matter provides the gravitational scaffolding that holds galaxies and galaxy clusters together. Dark energy sets the overall expansion rate and determines how quickly structures can grow. Ordinary matter fills in the visible components that we can observe directly. Understanding this early history is crucial for interpreting the universe we see today. Every galaxy, every star, and every planet bears the imprint of processes that began in the first moments after the Big Bang and were shaped by the invisible influence of dark matter and dark energy during the universe's infancy. The cosmic microwave background radiation, which we can observe today as the afterglow of the Big Bang, preserves a detailed snapshot of the universe as it existed just 380,000 years after its birth. The subtle patterns in this radiation reveal the distribution of dark matter and the seeds of cosmic structure at the moment when ordinary matter was first freed to begin forming the complex cosmos we inhabit. Future observations of the most distant galaxies, those we see as they existed when the universe was very young, continue to reveal new details about how dark matter and dark energy shaped cosmic evolution during its earliest and most dynamic phases. Each new discovery adds another piece to the cosmic puzzle, helping us understand how the invisible forces that dominate our universe guided its transformation from primordial simplicity to the rich complexity of today. In the first moments of the universe, these unseen forces began to shape its destiny, setting in motion the cosmic processes that would eventually lead to stars, planets, and life itself. As scientists have grappled with the profound mysteries of dark matter and dark energy, they have been forced to venture into realms of theoretical physics that push the boundaries of human imagination. The search for explanations has led to some of the most exotic and speculative ideas in the history of science, concepts so strange and revolutionary that they challenge our most basic assumptions about the nature of reality itself. These theoretical explorations represent humanity's attempt to comprehend forces that operate on scales vastly beyond our everyday experience, yet somehow determine the fate of everything we can see. The theories that have emerged from this quest range from elegant mathematical frameworks to wild speculations that read like science fiction, yet each represents a serious attempt to explain the inexplicable. One of the most ambitious theoretical frameworks attempting to explain both dark matter and the fundamental forces of nature is called supersymmetry. This beautiful mathematical theory proposes that every known particle in the universe has a corresponding partner particle with slightly different properties. For every electron, there would be a selectron. For every quark, there would be a squark. For every photon, there would be a photino. Supersymmetry emerges naturally from attempts to unify the fundamental forces of nature into a single theoretical framework. When physicists try to combine quantum mechanics with Einstein's theory of relativity at the highest energy scales, they encounter mathematical problems that seem to require the existence of these supersymmetric partner particles to resolve. Many of these supersymmetric particles would be perfect candidates for dark matter. They would be stable over cosmic timescales. They would interact only weakly with ordinary matter, and they would have been produced abundantly during the hot, dense conditions immediately after the Big Bang. The lightest supersymmetric particle, often called the neutralino, has become one of the leading theoretical candidates for dark matter. The appeal of supersymmetry lies not only in its potential to explain dark matter, but also in its ability to address several other deep puzzles in particle physics. Supersymmetry could help explain why the fundamental forces have the particular strengths they do, why certain particles have the masses they possess, and how gravity might eventually be unified with the other forces of nature. However, despite decades of searching, no supersymmetric particles have ever been detected in particle accelerator experiments. The Large Hadron Collider, which was partly built to discover evidence of supersymmetry, has found no trace of these hypothetical particles, despite probing energy scales where they were expected to appear. This absence of evidence has forced theorists to consider more exotic versions of supersymmetry, in which the partner particles are much heavier and harder to detect than originally predicted. While these models can still potentially explain dark matter, they require increasingly complex and fine-tuned theoretical frameworks that some physicists find less appealing than the original elegant formulations. Another revolutionary theoretical framework that could potentially explain dark matter and dark energy involves the existence of extraspatial dimensions beyond the three we directly experience. While we can move freely in 3 dimensions of space, advanced theories suggest that there might be additional dimensions that are somehow hidden from our perception. String theory, which attempts to describe all fundamental particles as tiny vibrating strings rather than point-like objects, requires the existence of 6 or 7 additional spatial dimensions for its mathematical consistency. These extra dimensions would be compactified or rolled up so tightly that they would be invisible at the scales we can currently probe. In these higher dimensional theories, dark matter could consist of ordinary particles that are trapped in the extra dimensions and can only interact with our 3-dimensional world through gravity. Since gravity is the only force that can propagate freely through all dimensions, this would explain why dark matter exerts gravitational effects but remains invisible to electromagnetic radiation. Dark energy could also arise from the geometry and dynamics of these extra dimensions. If the extra dimensions are slowly expanding or contracting, this could create an effective cosmological constant that drives the acceleration of our 3-dimensional space. Alternatively, fields that exist in the higher dimensional space could leak energy into our dimensions, manifesting as dark energy. The mathematical complexity of these higher dimensional theories is staggering, requiring advanced techniques from abstract mathematics and theoretical physics. Yet they offer tantalizing possibilities for unifying all the forces of nature, including gravity, into a single theoretical framework that could explain not only dark matter and dark energy, but the fundamental structure of reality itself. Some of the most speculative ideas about dark matter and dark energy involve the possibility that our universe is just one of countless others in a vast multiverse. In these scenarios, the properties of dark matter and dark energy in our particular universe might be determined by chance, representing just one possible outcome among an infinite array of possibilities. Cosmic inflation, the period of exponential expansion in the first moments after the Big Bang, could have created multiple bubble universes, each with different physical laws and different amounts of dark matter and dark energy. Most of these universes would be unsuitable for the development of complexity and life, but we naturally find ourselves in one of the rare universes where the conditions are just right. This anthropic explanation for dark matter and dark energy is controversial because it seems to give up on finding fundamental physical reasons for why these components have their observed properties. Instead, it suggests that they simply happen to have the right values in our universe because we exist to observe them. However, some versions of multiverse theory make testable predictions about the statistical distribution of dark matter and dark energy properties across different universes. If these predictions could be verified through improved observations of our own universe, they might provide indirect evidence for the existence of other cosmic realms beyond our direct observation. Quantum mechanics itself might hold the key to understanding dark energy through the mysterious properties of the quantum vacuum. According to quantum field theory, even completely empty space is filled with virtual particles that constantly appear and disappear on incredibly short timescales. These quantum fluctuations should contribute an energy density to empty space that could act as a cosmological constant. The problem is that when physicists calculate the expected magnitude of this vacuum energy using known principles of quantum mechanics, they get answers that are incomprehensibly larger than the observed dark energy density. This discrepancy, known as the cosmological constant problem, represents one of the worst failures of theoretical physics. Some theorists have proposed that unknown quantum mechanical effects might suppress most of the vacuum energy, leaving behind only the tiny residual amount we observe as dark energy. These suppression mechanisms would require new physics beyond the standard model of particle physics, possibly involving exotic quantum states or modifications to quantum field theory itself. Other approaches suggest that the vacuum energy might indeed be enormous, but that it is somehow screened or hidden by additional fields or forces that we have not yet discovered. In these models, what we observe as dark energy might be just the tip of an iceberg of vacuum energy that is mostly invisible to our measurements. Modified theories of gravity represent another class of speculative explanations for both dark matter and dark energy. Instead of invoking new forms of matter and energy, these theories propose that Einstein's general relativity requires modification when applied to the largest cosmic scales or the lowest acceleration environments. Some modified gravity theories suggest that gravitational attraction becomes stronger than Einstein predicted when dealing with the weak gravitational fields found in galaxy outskirts. This enhanced gravity could explain galaxy rotation curves without requiring dark matter. Other modifications propose that gravity becomes repulsive under certain conditions, potentially explaining cosmic acceleration without dark energy. The challenge for modified gravity theories is that they must reproduce all the successes of Einstein's theory in the solar system and other well-tested environments, while producing new effects only in the specific circumstances where dark matter and dark energy are inferred. Constructing theories that can satisfy all these constraints has proven extremely difficult. Emergent gravity theories take an even more radical approach, suggesting that gravity itself might not be a fundamental force, but rather an emergent phenomenon arising from more basic underlying physics. In these models, what we interpret as gravitational attraction might actually result from the quantum entanglement of matter across cosmic scales. If gravity is indeed emergent rather than fundamental, then the apparent need for dark matter and dark energy might reflect our incomplete understanding of how gravity arises from quantum mechanics. These theories are still in their infancy and face enormous challenges in making concrete predictions that can be tested against observations. The possibility that dark matter and dark energy are connected to each other through some underlying unified physics has inspired numerous speculative models. Perhaps both components arise from the same field that behaves differently under different conditions, or maybe they represent different phases of the same underlying substance. Chameleon fields represent one example of such unified approaches. These hypothetical fields could act like dark matter in dense environments where they become heavy and clump together, but behave like dark energy in low-density regions where they become light and create repulsive effects. Such fields could potentially explain both mysteries with a single theoretical framework. Mirror matter theories propose that dark matter consists of an entire parallel sector of particles that mirror our own, but interact with ordinary matter only through gravity. In these models, there could be mirror atoms, mirror stars, and even mirror planets existing alongside our visible universe, but remaining completely invisible, except for their gravitational effects. The study of quantum information and the holographic principle has opened new avenues for understanding dark energy. Some theories suggest that information stored on the boundaries of space might determine the properties of dark energy within that space. In these holographic models, the acceleration of cosmic expansion could arise from the way information is encoded in the fabric of spacetime itself. Advances in our understanding of quantum entanglement and quantum field theory in curved spacetime continue to generate new ideas about the nature of dark matter and dark energy. The intersection of quantum mechanics, general relativity, and information theory represents a frontier where revolutionary discoveries about these cosmic mysteries might emerge. The search for theoretical explanations has also been driven by the hope that understanding dark matter and dark energy could unlock new technologies or reveal new fundamental principles that could transform human civilization. The energy scales and physical processes involved in these phenomena are so extreme that their full understanding might lead to breakthroughs we cannot currently imagine. As our experimental capabilities continue to improve and our theoretical understanding deepens, some of these speculative ideas may eventually be tested against observation. Others may be ruled out by future discoveries, while entirely new theoretical frameworks may emerge that we have not yet conceived. Perhaps the answer lies in realms beyond our current understanding, in new theories and new ideas yet to be discovered. The search continues to push the boundaries of human knowledge, venturing into territories where imagination and rigorous scientific reasoning must work together to illuminate the deepest mysteries of existence. The invisible forces that dominate our cosmos today will continue to shape the universe for countless billions of years into the future, determining not only how cosmic structures evolve, but ultimately deciding the final fate of everything that exists. As we peer forward through time, guided by our understanding of dark matter and dark energy, we can begin to glimpse the extraordinary destiny that awaits our universe over timescales so vast that they challenge human comprehension. The future evolution of the cosmos depends crucially on the nature of dark energy and how its influence will change as the universe continues to expand. If dark energy remains constant, as current observations suggest, then its dominance over the universe will only grow stronger with time. As ordinary matter and dark matter become increasingly diluted by cosmic expansion, dark energy will maintain its density, eventually becoming the only significant component in a universe that grows ever more empty and cold. This scenario leads to what cosmologists call the Big Freeze, a future in which the universe expands forever at an accelerating rate, gradually separating all cosmic structures until they become isolated islands in an ocean of empty space. The timeline for this cosmic evolution unfolds over periods so immense that the entire history of the universe to date represents merely the opening chapter of an epic story that will continue for an almost infinite duration. In the relatively near future, cosmically speaking, dark energy will begin to have increasingly dramatic effects on the growth of cosmic structure. Currently, dark matter halos can still grow through gravitational attraction as smaller structures merge together to form larger ones. However, as dark energy becomes more dominant, it will become increasingly difficult for gravity to overcome cosmic acceleration and pull matter together into new structures. Within the next few billion years, dark energy will effectively halt the formation of new galaxy clusters. The cosmic web of dark matter filaments that currently connects galaxies across vast distances will begin to stretch and weaken as accelerating expansion pulls these structures apart. Galaxy clusters will become the largest structures that ever form in our universe, frozen in time as cosmic expansion carries them beyond each other's gravitational reach. Individual galaxies will initially be protected from cosmic acceleration because their internal gravity is strong enough to hold them together against the influence of dark energy. Our own Milky Way galaxy, bound together by its dark matter halo, will continue to rotate and evolve much as it does today. In fact, the Milky Way is destined to merge with the nearby Andromeda galaxy in approximately 4.5 billion years, creating a larger elliptical galaxy that astronomers have playfully named Milkomeda. This galactic merger will be one of the last major cosmic events in our local region of space. After Milkomeda forms, the combined galaxy will find itself increasingly isolated as cosmic expansion carries all other galaxies beyond the horizon of gravitational interaction. The local group of galaxies, which currently includes the Milky Way, Andromeda, and several dozen smaller companions, will become a gravitationally bound island universe surrounded by empty space. As billions of years pass, the stars within Milkomeda will continue to burn their nuclear fuel and eventually die, one by one. The most massive stars will live only a few million years before exploding as supernovae, while smaller stars like our Sun will shine for billions of years before evolving into white dwarf stars. The smallest red dwarf stars, with masses less than half that of our Sun, will continue burning hydrogen for trillions of years, far longer than the universe has currently existed. These red dwarf stars will become the last beacons of light in an increasingly dark universe. As more massive stars exhaust their fuel and fade away, red dwarfs will dominate the stellar population, providing the only source of energy for any remaining planets or potential life forms. Eventually, even these long-lived stars will exhaust their hydrogen fuel and fade to darkness, leaving behind cold white dwarf remnants. The role of dark matter during these future epochs remains somewhat mysterious because we still do not know whether dark matter particles are completely stable or whether they might very slowly decay over cosmic time. If dark matter is absolutely stable, then dark matter halos will persist essentially forever, continuing to provide the gravitational scaffolding that holds galaxies together even after all the stars have died. However, if dark matter particles have finite lifetimes and decay over periods of many trillions of years, then even the dark matter halos themselves will eventually evaporate. This would leave behind only the compact remnants of dead stars, black holes, and any surviving planets, floating freely through an expanding universe with no gravitational structures to bind them together. The evolution of black holes represents one of the most fascinating aspects of the universe's far future. These exotic objects, formed when massive stars collapse under their own gravity, will be among the longest-lived structures in the cosmos. While ordinary matter can escape from the vicinity of black holes through various processes, the black holes themselves are predicted to evaporate extremely slowly through a quantum mechanical process discovered by Stephen Hawking. Hawking radiation causes black holes to gradually lose mass by emitting particles and energy into the surrounding space. However, this process is incredibly slow for black holes of stellar mass or larger. A black hole with the mass of our Sun would take approximately 10 to the power of 67 years to evaporate completely, a period so vast that it makes the current age of the universe seem like an instant in comparison. The largest black holes, with masses billions of times greater than our Sun, will persist for even longer periods, continuing to slowly evaporate through Hawking radiation for times that approach 10 to the power of 100 years. These supermassive black holes, which currently reside at the centers of most galaxies, will be among the very last objects to disappear from the universe. During the black hole era, which will last for most of the universe's future existence, these gravitational behemoths will occasionally encounter and consume any remaining matter that drifts too close. White dwarf stars, neutron stars, and any surviving planets will eventually be swallowed by black holes through random gravitational encounters over incredibly long timescales. As black holes consume the last remnants of ordinary matter, they will briefly grow in mass before resuming their slow evaporation through Hawking radiation. The energy released during this evaporation process will provide the only source of heat and light in a universe that has otherwise grown completely cold and dark. If dark energy continues to behave as a cosmological constant, maintaining constant density as the universe expands, then cosmic acceleration will persist throughout all these future epochs. The expansion rate will continue to increase, eventually carrying distant regions of space away from each other faster than the speed of light. This does not violate relativity, because space itself is expanding rather than matter moving through space. However, some theoretical models suggest that dark energy might not remain constant forever. Quintessence models predict that dark energy could evolve over time, potentially growing stronger or weaker as the universe ages. If dark energy continues to strengthen, it could lead to an even more dramatic future called the Big Rip. In the Big Rip scenario, dark energy becomes so powerful that it eventually overcomes all other forces in the universe, including the electromagnetic forces that hold atoms together and the nuclear forces that bind protons and neutrons. This would lead to a catastrophic finale in which cosmic acceleration becomes so extreme that it tears apart galaxies, stars, planets, and eventually atoms themselves. The timeline for a big rip depends on how rapidly dark energy strengthens over time. Some models predict that this cosmic catastrophe could occur in as little as 20 billion years, while others suggest it might take much longer. If the Big Rip is indeed the universe's destiny, then all the cosmic structures we see today, including Earth and everything on it, would be torn apart in a final moment of infinite acceleration. Alternatively, if dark energy weakens over time rather than strengthening, the universe might eventually return to a phase dominated by matter and gravity. In such scenarios, cosmic expansion could slow down, halt, and even reverse, leading to a big crunch in which all matter collapses back together in a mirror image of the Big Bang. A big crunch would compress all matter and energy back into an incredibly dense state, potentially creating conditions similar to those that existed immediately after the Big Bang. Some cosmologists have speculated that this could lead to a cyclic universe that alternately expands and contracts over infinite periods of time, with each cycle potentially creating new physical laws and different amounts of dark matter and dark energy. The possibility of cyclic universes raises profound questions about the ultimate nature of time and existence. If the universe has undergone infinite cycles of expansion and contraction, then our current epoch might be just one of countless similar phases that have occurred throughout eternity. Each cycle could produce different types of stars, planets, and perhaps even different forms of life and consciousness. Current observations strongly favor continued acceleration and eternal expansion rather than eventual collapse. But our understanding of dark energy remains so limited that dramatic surprises cannot be ruled out. Future observations of distant supernovae, cosmic microwave background radiation, and large-scale structure will help determine which of these cosmic destinies awaits our universe. The fate of any life or intelligence that might exist in the far future depends critically on the behavior of dark energy and the ultimate destiny of cosmic expansion. If the universe expands forever while cooling to near absolute zero, any surviving civilizations would need to develop technologies that could harness the incredibly sparse energy sources available in such an environment. Theoretical physicists have speculated about the possibility of civilizations that could survive by carefully managing the energy released by evaporating black holes, or by finding ways to extract energy from the quantum vacuum itself. Such technologies would require mastery of physics that extends far beyond our current understanding, potentially involving the manipulation of space and time on cosmic scales. The search for understanding dark energy has become more urgent as astronomers have realized that its effects will dominate the universe's future evolution. Current and planned astronomical surveys are designed to measure dark energy's properties with unprecedented precision, looking for any signs that its strength or behavior might change over time. Space-based telescopes optimized for studying dark energy will observe millions of distant galaxies and supernovae to map the expansion history of the universe in exquisite detail. Ground-based surveys will measure the positions and properties of billions of galaxies to study how cosmic structures have evolved under dark energy's influence. These observations may reveal whether dark energy truly behaves like a cosmological constant, or whether it represents something more exotic and dynamic. The answer will determine not only the ultimate fate of our universe, but also whether the current epoch of cosmic acceleration represents a permanent feature of reality or merely a temporary phase in a more complex cosmic evolution. As we stand at this moment in cosmic history, when stars still shine brightly and galaxies dance together in cosmic clusters, we are witnessing the universe during one of its most active and interesting phases. The future evolution determined by dark matter and dark energy will carry the cosmos toward destinies we can barely imagine, guided by invisible forces that remain among the deepest mysteries in all of science. The forces that bind and stretch the universe are still mysteries, but they will continue to shape everything that exists for countless ages to come. Understanding their nature and predicting their future behavior represents one of the greatest challenges and opportunities for human knowledge as we seek to comprehend our place in an evolving cosmos that grows stranger and more wonderful with each new discovery. As we reach the end of our journey through the hidden universe, we find ourselves confronting a profound and humbling truth about the nature of existence itself. The cosmos we inhabit is far stranger, far more mysterious, and far more wonderful than our ancestors could have ever imagined when they first looked up at the night sky and wondered about their place among the stars. We have traveled together through the story of dark matter and dark energy, two invisible forces that together make up 95% of everything that exists, yet remain as elusive and mysterious today as they were when scientists first discovered evidence of their presence. These cosmic ghosts shape every galaxy, influence every star, and determine the ultimate destiny of the universe itself, all while remaining completely hidden from direct observation. The discovery of dark matter began with a simple observation that galaxies were moving too fast to hold together based on the visible matter alone. What started as an astronomical curiosity evolved into the recognition that most of the matter in the universe consists of particles that interact with ordinary matter only through gravity, creating an invisible scaffolding that binds the cosmos together. Dark energy emerged from an even more surprising discovery, when astronomers expecting to measure the slowing of cosmic expansion instead found that the universe is accelerating, driven apart by a mysterious force that appears to be woven into the very fabric of space itself. This revelation forced scientists to confront the existence of a component that dominates the energy budget of the universe, yet defies every intuition about how matter and energy should behave. Together, these discoveries have revolutionized our understanding of the cosmos and our place within it. We now know that the atoms in our bodies, the planets orbiting distant stars, and every point of light visible in our most powerful telescopes represent just a tiny fraction of what actually exists. The visible universe floats like foam on an ocean of invisible matter and energy that we are only beginning to comprehend. The search for these hidden components has driven humanity to the limits of technological capability and theoretical imagination. Scientists have built detectors deep underground, hoping to catch the rare interactions of dark matter particles with ordinary matter. They have constructed particle accelerators capable of recreating conditions from the first moments after the Big Bang. They have launched telescopes into space to map the distribution of dark matter through its gravitational effects and to trace the expansion history of the universe with unprecedented precision. Yet despite decades of intensive effort using increasingly sophisticated instruments and techniques, dark matter and dark energy continue to guard their secrets. Every experiment designed to detect them directly has come up empty. Every theoretical framework proposed to explain their nature faces significant challenges when confronted with observations. The universe's greatest mysteries remain unsolved, taunting us with their proximity yet persistent invisibility. This ongoing mystery represents both a humbling reminder of the limits of human knowledge and an inspiring testament to our species' insatiable curiosity about the nature of reality. The fact that we can detect the influence of invisible forces throughout the universe, map their distribution, and predict their effects on cosmic evolution demonstrates the remarkable power of scientific reasoning and observation. At the same time, the persistent elusiveness of dark matter and dark energy reminds us that the universe still holds secrets that may require entirely new ways of thinking about space, time, matter, and energy. The solutions to these cosmic puzzles might demand revolutionary advances in fundamental physics that could transform our understanding of reality itself. The implications of dark matter and dark energy extend far beyond academic cosmology. These invisible components will determine the future evolution of every structure in the universe, from the smallest galaxies to the largest clusters. They will decide whether the cosmos expands forever into cold, dark emptiness or experiences some other dramatic transformation that we cannot yet imagine. If we could somehow remove dark matter from the universe, galaxies would fly apart and stars would never have formed. If we could eliminate dark energy, cosmic expansion might halt and reverse, leading to a catastrophic collapse. The delicate balance between these invisible forces and ordinary matter has created the conditions necessary for the emergence of complexity, structure, and ultimately life itself. The anthropic perspective suggests that we find ourselves in a universe with exactly the right amounts of dark matter and dark energy, precisely because these are the conditions that allow for the existence of observers like ourselves. In this view, the apparent fine-tuning of cosmic parameters reflects not fundamental physical laws, but rather a selection effect among many possible universes. Whether or not this interpretation is correct, the study of dark matter and dark energy has revealed the remarkable interconnectedness of cosmic evolution. The formation of the first stars depended on dark matter halos to provide gravitational wells for gas to collect. The current acceleration of expansion depends on dark energy, overwhelming the attractive influence of all forms of matter. The future habitability of the universe depends on how these components will evolve over cosmic time. The search for dark matter and dark energy has also fostered unprecedented international collaboration among scientists from around the world. The challenges involved in detecting these elusive components are so great that they require the combined efforts of physicists, astronomers, engineers, and computer scientists working together across national boundaries and disciplinary divisions. This collaborative approach has driven innovation in detector technology, data analysis techniques, and theoretical modeling that extends far beyond the original goals of dark matter and dark energy research. Technologies developed for underground dark matter detectors have found applications in medical imaging and national security. Statistical methods created for analyzing cosmic survey data have influenced fields ranging from machine learning to financial modeling. The ongoing search continues to push the boundaries of what is technologically possible. Next-generation experiments will be orders of magnitude more sensitive than current detectors, capable of probing interaction rates so low that they approach fundamental quantum mechanical limits. Future space missions will map the distribution of dark matter and the effects of dark energy with unprecedented precision, potentially revealing subtle variations that could provide crucial clues about their nature. New theoretical frameworks continue to emerge from the intersection of particle physics, cosmology, and quantum mechanics. String theory, extra dimensions, supersymmetry, and modified gravity all offer potential pathways toward understanding these cosmic mysteries. Each new idea represents another attempt to bridge the gap between what we observe and what we can explain using known physics. The possibility that dark matter and dark energy might be connected through some deeper underlying principle remains an active area of theoretical research. Perhaps both components arise from the same field or force, operating under different conditions. Perhaps they represent different aspects of a more fundamental description of space and time that we have not yet discovered. As we continue this cosmic detective story, we are essentially trying to read the autobiography of the universe itself, deciphering clues written in the cosmic microwave background, the distribution of galaxies, and the light from distant supernovae. Each new observation adds another piece to a puzzle of almost unimaginable complexity and beauty. The journey to understand dark matter and dark energy represents more than just an attempt to solve specific scientific problems. It embodies humanity's relentless drive to comprehend the deepest aspects of existence, even when those aspects remain stubbornly hidden from direct observation. This quest reflects our species' unique capacity for curiosity, creativity, and collaboration in the face of seemingly impossible challenges. Young scientists around the world continue to be inspired by these mysteries, choosing to dedicate their careers to the search for answers that may not come for decades or even centuries. Their work represents an investment in the future of human knowledge, a commitment to understanding that transcends individual lifetimes and national boundaries. The story of dark matter and dark energy is still being written. Future chapters may reveal the true nature of these invisible components, potentially revolutionizing our understanding of physics and cosmology. Alternatively, they may uncover even deeper mysteries that challenge our assumptions about the nature of scientific inquiry itself. Whatever discoveries await us, the search for dark matter and dark energy has already transformed our view of the cosmos and our place within it. We now know that we live in a universe dominated by invisible forces, where the familiar matter of stars and planets represents just a small perturbation in a vast ocean of the unknown. This knowledge brings with it a sense of cosmic humility, reminding us that despite all our technological achievements and scientific understanding, we remain essentially children playing at the edge of an infinite ocean of mystery. Yet it also brings wonder and excitement, knowing that the universe continues to surprise us and that there are always new discoveries waiting to be made. Though dark matter and dark energy remain elusive, they shape everything we see and determine the future of everything that will ever exist. As we continue our search for understanding, we step closer to the mysteries that define the cosmos, driven by the conviction that the universe's greatest secrets are waiting to be discovered by those who dare to look for them in the darkness between the stars. The universe may be mostly dark and unseen, but its story continues to unfold through the curiosity and determination of those who seek to understand the invisible forces that bind and shape all of existence. In this ongoing quest for knowledge, we find meaning, purpose, and a connection to something far greater than ourselves.